If you have ever been on a high-speed boat ride before, there is a big chance that you got seasick, or you couldn't move around the boat much in order to avoid from flipping over. These very fast boats are super popular both for recreational and military uses, but due to their high speeds, these boats have a very complex interaction with the water they move over. That means when a planing boat is moving at a high speed, unpredictable or dangerous responses can occur.
When you have a boat that's operating in waves, you have to worry about the fact that the boat isn't just sitting there and the wave going by it. The boat actually has to move in relationship to these waves coming in. So you can have a problem where, here's my wave and here's the boat coming in, and how quickly they actually meet depends on how fast the wave is moving, but also how fast the boat is moving.
Naval architect Carolyn Judge is trying to understand all of the possible interactions between the boat and water so that she can build more efficient boat designs, or boats that have different shapes and might be more predictable in water.
We don't yet know enough to do that in a way that makes sense. So that's where we're hopefully going.
Judge is also modeling how the boat interacts with waves and water so that engineers can create a safer boat, or a boat that can modify the controls of the driver to avoid collisions or great impacts.
If we can model with math what is happening when the boat is going through the waves, then we would be able to design a system to basically analyze it the same way that the driver's brain does it through experience.
She designs boat models that are tested in a huge water tank in the Naval Academy.
We can go take this model and put it in the tank and run it down the tank at speeds so that it acts like a planing boat. And when I do that, what I'm looking at is what happens to the forces due to that flow going over the bottom if the boat isn't perfectly upright. For this particular boat, I have a force that's measuring the upward force on the boat and also measuring the sideways force on the boat. And over here, the one that's attached to the side is measuring the force required. It's really a moment required to oscillate it back and forth. And so at any given point in time, I know the angle of the model, in other words, how much it's tipped. I know the moment causing that. I know the upward force on the model. I know the sideways force on the model, and the carriage measures how fast it's going.
Judge explains that a good boat must be stable.
What we talk about as a boat to stay upright is called stability. In other words, you want it to stay upright even when something comes along that gives it a little bump. And why it stays upright is the tricky part.
A boat has a lifting force that is holding it up because it pushes water out of the way. This force is called buoyancy and pushes up at a point called the center of buoyancy. There is also a force called gravity, pushing down on the boat due to its weight. For a stable boat, the center of buoyancy is directly aligned with the center of gravity. For the boat to be stable, these forces have to stay lined up, even when the boat undergoes crazy jumps and tilts. Carolyn figures out what needs to be done in either the boat's design or controls to keep these two forces lined up.
If I have an upward force acting here and a downward force acting here, it tips my boat over, and that's unstable. So when you're designing a boat, you have to make sure that doesn't happen. When you have a boat like this, what's most important is where the height, in other words, how high up that center of gravity is. If anyone's ever been on a rowboat and you stand up and start walking around, the boat starts getting really tippy, right? It feels a lot less stable. You can easily end up in the water or have everybody end up in the water. So when you want to keep the boat stable, you want that center of gravity to be as low down as possible. If you imagine that block is, your cargo or passengers, and if a wave comes along and knocks my boat to the side, it returns back to where it was originally. That's stable. If, however, my boat was loaded like this with the center of gravity up high, and that same little wave came along and bumped my boat slightly, it would run away, and that's unstable.
What gets even more tricky is when the boat is propelled by something other than just the buoyancy force. As in a planing boat, the propeller generates the flow of water under the boat, causing the lift.
It's a little bit more difficult to know where that force is acting on the boat. And therefore, it's a little bit more difficult to know where you need it to be to line up with your center of gravity. For a really good design, you want to be able to know exactly where you need that center of gravity to be and where your center of lift actually is acting. And that's where we don't yet know. That's what we're learning. We're trying to understand.
Now you can be a naval engineer. Check out the activities on the Curiosity machine and build your own boat design.